Hello, wonderful people. Here we are, chapter 14, satellite motion. We're moving on to section 4, energy conservation and satellite motion. So this is all about kinetic and potential energy. Uh, so here is the point. The sum of the kinetic and potential energy of a satellite is constant at all points along an orbit. So, do you remember we call that sum mechanical energy from back in chapter 8, I think? So, we'll talk more about that in this slide. So, let's get into it. Why isn't it moving? There we go. Moving objects have kinetic energy. Kinetic energy is 1/2 mv squared. So, that's how you figure out how much kinetic energy they have. An object above Earth's surface has potential energy due to its position. Potential energy is mgh, mass times the acceleration of gravity times height. So if you raise it up above Earth's surface, then you're giving it potential energy. So everywhere in an orbit, a satellite has both kinetic and potential energies. In a circular orbit, the distance between a planet's center and the satellite center is constant. So if the height's not changing, then the PE of the satellite is the same everywhere in orbit. And by law of conservation of energy, the kinetic energy is also constant. So the speed is constant, the kinetic energy is constant, the height's not changing, so the PE is constant. But like I said, there are no circular orbits. They're all elliptical. So there's the picture showing constant height, constant PE, constant KE. Here's where we are in the real world. In an elliptical orbit, both speed and distance vary. So here are two words you're going to need to know for this chapter. Apogee. The apogee is the point where in the satellite's orbit where it's the furthest from the center of the Earth. And the perigee, perigee, I never get that right, perigee, is the point where it's closest to the center of the Earth. So let's get to the picture. Here we go. The perigee is where it's the closest to the center of the Earth, and the apogee is where it's furthest. So we've seen this on all our in our labs and stuff along the way. Right here at the perigee is where it's moving the fastest. So the fastest means the kinetic energy is the biggest and the potential energy is the smallest because the height from the center of the satellite to the center of the Earth is shorter. Over here, the height is really high, so the potential energy is really high. But the speed is really slow. So that's small ke plus big PE is our constant mechanical energy, ME. Both are medium, you get the same ME. One big, one small, you get the same mechanical energy. Now there's the wonderful picture. Here it is put into words. The potential energy is greatest when the satellite is at the apogee and least when the satellite is at the perigee. The kinetic energy will be least when the potential energy is most, and the kinetic energy will be most when the potential energy is least. At every point in the orbit, the sum of the kinetic and potential energies is constant. At all points on the orbit, except at the apogee and perigee, a component of gravitational force is parallel to the direction of satellite motion. So a component of it is parallel. This component changes the speed of the satellite. So the component of force times distance moved equals change in the kinetic energy. That's a little further than I would want to go. If you understand that, great. We're talking about work here. Force times distance. When a satellite gains altitude and moves against this component, its speed and kinetic energy decrease. The decrease continues up to the apogee. Once past the apogee, the satellite moves in the same direction as the component, and the speed and kinetic energy increase. So here's what we're talking about. There's the force of gravity pushing it in this direction. If you break that up into the component that is tangent to the circle and perpendicular to the circle, you can see there's some force going along where the motion of the satellite is. It's moving in that direction. Moving in that direction. So there's some gravitational force in that direction. So if there's a gravitational force, it's getting faster. So that's why it accelerates, accelerates, accelerates faster, faster, faster. And right there, when it's at the apogee, there is no horizontal component. It's all straight in. And then it's, do I have a picture of the opposite case? I do not. Ooh, darn it. On this side, while it's moving up, the component force of gravity is down. So that's why it's getting slower going up. And we can leave it at that. The orbital path of the satellite is shown in the sketch. In which of the positions A through D does the satellite have the most kinetic energy? The most kinetic energy is at, no, kinetic is there, A. And the most potential, where the height is the most, C. And the most total energy, well, total energy never changes. So total energy is a constant everywhere on the orbit. Oh, and there's the answer written out. Thank you. So, what is the relationship between the kinetic and potential energy of a satellite motion? The total energy is the same anywhere in the orbit. There's the answer. So that is section 14.4. Next is Kepler, and we can stop here. Thank you very much.